successful embedded world, and we're into another engineering hour with Amesh Lakande. Amesh is going to be walking us today through MODBUS RTU Slave firmware on STM32. So really a great session to kick us back off and get us into the swing of things as we start going into some of the industrial protocols. Amesh, say hi.
Hi everyone.
Great. So for those of you who are new to the DevHeads community and our community events, you'll want to check us out. If you go to devheads.io or discord.gg/devheads, you'll be able to join the community, interface with experts like Amesh and others like Ming and Zach, who are great on embedded Linux and real-time software, and a whole host of others. If you are trying to build an embedded or IoT product, they and we collectively can help you get on your way. So feel free to check us out. Today, we're going to have a session that's called Engineering Hours that lasts about an hour. So Amesh will do some presentation for like 45 or 50 minutes, and then there'll be an opportunity for you to ask questions at the end and have Amesh respond in real time. So during the course of the event, don't be shy. Feel free to use the chat. If you're in the Livestorm Live event platform, there's also a questions tab. Feel free to use that. I'll be monitoring it. And if you're in another platform, like you're out on LinkedIn or YouTube or Facebook, we'll also hop over there too and say hi. Feel free to put your questions or comments in there, and we'll aggregate them back and make sure they get in front of Amesh so he can answer questions at the end of the hour. Just a quick note that this is also the first of a couple part series, so you'll want to check back. We'll have more information about part 2 at the end of the event after Amesh is all done. But really quickly, let's jump into some housekeeping things to make sure that you have a good event experience. If you run into issues with the stream, like you're having trouble viewing it or hearing the audio or anything else related to the broadcast, there are a couple of things that we recommend that you try before giving up or blowing up the chat. Number one, check your bandwidth. So if you use a service like speedtest.net, you should be able to see whether you're pulling a decent amount of bandwidth down, and a decent amount in this case is 5 megabits per second. If you're underneath that threshold, you might have problems with the stream. So see if you can get on another network. If you're using Discord, try quitting the application and come back in. We found that if you're using like the desktop or the mobile app version of Discord and it's not up to date, that can cause some problems. So we do recommend using the web browser version. If you're in the Livestorm Live event platform, that shouldn't be an issue because it's web only. Otherwise, you can use Discord from the web itself, and wherever else you are, we'd recommend the same. Just try using the web app because it's more up to date. Anything that might be consuming bandwidth, you should close. Anything that might be consuming a lot of memory, you should close. And then if all that fails, feel free to direct message me. I'm either at TechElu or at Brandon Lewis, depending on which platform you're in, and I'll come check it out and see if I can give you some help. So I'm going to drop some more information about where you can find resources from the DevHeads community, but I know you didn't come here to have me tell you about how to use tools. You came here to have Amesh explain a little bit more about Modbus and STM on STM32. So at this point, I'm going to hand it off to Amesh. Amesh, take it away.
Hi everyone, I hope you all are excited to learn about the Modbus and how to implement the Modbus RTU Slave firmware on STM32 microcontroller. So basically, by the end of the session, we would end up making STM32 microcontroller, especially the nuclear board that I will be using to convert it as a Modbus compatible device. So the direction today is we're going to start off with an overview of a Modbus protocol just to understand why Modbus is so popular and how it makes its significant contribution. Then we're going to talk about the available standards because there are a different standard inside the Modbus protocol. I mean, you can say different types of Modbus. You can just assume, and we'll get into that bit later. Then I will going to talk about the Modbus memory areas. These are basically Modbus registers, and basically working with Modbus protocol with any Modbus device is to work with the Modbus registers, right? And we'll get into that here. And then we'll look into the Modbus RTU frame format because, like how the data is represented into the protocol is very important. And this is where we have an opportunity to look into the data frame, how the data frame is organized into the Modbus protocol. And then we'll look at the function code. Function codes are very important in Modbus because they decides what exactly we want to do with the devices. Then we'll dive into Modbus master simulator, I will be using a Simply Modbus simulator, which is very popular, and we'll get into that how to use to communicate with the slave devices. And then I will show you a live demo where we will implement the Modbus RTU firmware on STM32 microcontroller. And then we'll summarize all the things that we have seen so far. And towards the end of the session, I will take a question if you have any. And in case if we run out of a time, because this is very big topic, feel free to drop your question inside the Discord server. We have a dedicated channel for the communication stack. It's called Fieldbus. So feel free to drop your questions there. Now, let's just start with Modbus. Modbus is an open standard. That means if you want to use Modbus as a protocol to develop your product, you can freely use it. The Modbus RTU commands are simple. I think it's because the Modbus as a protocol developed very early on in the automation. I mean, first few protocols, I would say. I mean, the popular one, widely adopted. So the command structure is very simple. Why? We'll get into that bit later. Then the Modbus has a simple data representation because the data representation is easy to work with. The Modbus frames is easy. And the way this Modbus protocol works, the Modbus devices works is using a request and response command structure. So you might have heard about it, like when you use a Modbus, you have a one device which is a Modbus master, and you have other device, let's say a Modbus slave. The way both communicate is the Modbus master sent the request to the slave device, and slave device will respond back. I mean, give the response back to the master device, and that's how the master and slave communicate, and data will be exchanged between two devices. That's basically. And by the way, the people who are coming from the web technologies, they know that HTTP protocol also works with request and response mechanism. So it would be amazing for the people who comes with a different perspective. But just on a quick note, Modbus works in request response mechanism. Now, if the Modbus is used with RS485 standard, then it allow us to have a differential communication. So it's use a differential pair. And in that case, you can have 32 nodes, Modbus slaves you can connect in multi-drop configuration. So what does this mean? This means if you use Modbus protocol, and if you use it with RS485, you can have one Modbus master can able to talk to multiple slave, and multiple slave would be up to 32 nodes you can able to communicate. So that's a great thing. If you use it Modbus protocol with RS232 standard, then you can have just a point-to-point communication. So one master can only talk to one slave. Now, the Modbus with RS485 provide noise immunity better than RS232. That's the reason why after a success of RS232, RS485 been adopted very widely, and it's become very successful because RS485 is capable to provide a better noise immunity into the factory environment when you connect a sensors. And probably you know that many of the sensors being used in the field environment in the factory, those are analog devices, and that's why they are very sensitive to the noise, and the accuracy you need for industrial application is very high. So RS485 provide you better noise immunity, and the very, very important thing for the embedded developer is it requires very little code space. So if you have a device which has, let's say, a 64 kilobytes of memory, or maybe 100 kilobytes of memory, just like this microcontroller. Look at this STM32 that I will be using. So if you have just a few 100 kilobytes of memory, you still can implement the Modbus core. I mean, Modbus firmware, you can write it and make this device, any device that you can code it and then make it as a automation app. Because very recently people started realizing that even with the smaller devices like a microcontroller, you can build an industry automation, or maybe the devices that can talk to industrial environment. Otherwise, earlier, I remember before 2009 and 2010, every time the industrial devices will be considered as a PLCs only, right? Logic controllers, and they are more powerful than the microcontroller. But anyways, the point here is, if you use a Modbus, Modbus can be implemented with very little code size, with very little memory. And that's a great thing to build automation application. Now, let's just talk about multi-slave configuration, because we talked like if we use a Modbus as a protocol, and we have, let's say, a one Modbus master device, can able to talk to multiple slaves. So in this picture here, you can see I took 5 microcontroller. So this 5 microcontroller, and every microcontroller like this one, this one, this one, every microcontroller has a dedicated slave ID. Now, what happens is in the Modbus communication, especially Modbus RTU, we'll get into that, the difference RTU and TCP. But in Modbus RTU protocol, every slave device, like every microcontroller, has a dedicated slave ID. So let's say if we have a master Modbus master device can able to talk to this microcontroller, it will call slave ID 1. Now, some people call slave ID, some people refer that as a slave address. It doesn't matter whether you call it as a slave ID or slave address, but it's the same thing. Let's say if the Modbus master want to talk to this microcontroller, the master microcontroller will send a request to this slave ID 05, right? So that means in the Modbus RTU protocol, for every slave device has a dedicated slave ID, so that master can able to talk to multiple slaves. Now remember these things. In the Modbus RTU, you can have only one master which can talk to multiple slaves. So there is only one master. That's why, and you don't have a multiple master, by the way, in the Modbus RTU. So I hope you get the point. In the multi-drop configuration, we have one Modbus master can talk to multiple slave, and multiple slave has a dedicated slave ID. That's how the master can talk to each device. Now let's just talk about available standards, because as I said, when we talk about Modbus in our mind as a Modbus standard, we get the thought of Modbus RTU, whether it's a Modbus RTU, or the second thought we get as a Modbus TCP IP, because these two Modbus protocols are very popular. So we're going to talk first about these two protocols, and then we'll go into the other standards inside the Modbus. Now, what does this Modbus RTU means? The RTU stands for Remote Terminal Unit. So Modbus RTU uses a serial communication. That's why if you look at the left side of this picture, Modbus RTU uses serial communication like RS-232, RS-485, and RS-422. Right? And if you look at the right side of the picture here, where we have the Modbus TCP IP, here we need Ethernet communication, right? So the Modbus TCP require Ethernet communication, wherein Modbus RTU just works fine with the serial communication. You can even use it with the UART communication. I hope you get the point. Like, the difference of Modbus RTU and Modbus TCP is that Modbus RTU needs a serial communication protocols, like it uses any standards from 232, RS-485, or 422. Anyone will work fine. But on the top, on the application side, you can see the Modbus application layer remains the same, whether it's a Modbus RTU or it's a Modbus TCP. Okay, so there are a few more differences. We'll get into that bit later. But right now, you just have to understand, when it's a Modbus RTU, it uses a serial communication protocol like RS-232, RS-485, and RS-422. And when it's a Modbus TCP, then it uses an Ethernet as a communication protocol. Now, apart from these two Modbus standards, there is one more called the Modbus ASCII. This is also a kind of popular one. You kind of see a lot of devices supports that. And most of the devices which support Modbus RTU, you may see the optional support for the Modbus ASCII as well. And then you have a Modbus Plus, which is basically a proprietary Modbus standard. You might see a lot of devices from the Schneider Electric support the Modbus Plus, and even the other devices. But I hope you get the point. Like, there is a Modbus RTU, Modbus ASCII, TCP, Modbus over TCP, UDP, and Modbus Plus. But two of them are very common, is RTU and the Modbus TCP. That's why we are focusing just today about Modbus RTU, and in the future we will implement the Modbus TCP IP. Okay, so let's just talk about the Modbus memory area, because whenever you want to communicate devices which supports the Modbus protocol, you basically I mean, let's just take an example. You have one Modbus master and you have other Modbus slave. Now, when Modbus master wants to talk to Modbus slave, it should know the memory address that it operates on. So in Modbus memory areas, we have this registers, you can say. It's called coils, discrete inputs, input register, and holding register. So these are the few things you can find into the memory region of any Modbus compatible device. I know you might wonder right now, what the hell is this? What is coil? What is discrete input? We'll get into that. Just hold on. So coil is basically a place in the Modbus memory which deals with a discrete output. So in this memory region of coils, you operate a discrete output, which is just a 1 bit. So let's say if you have a device, Modbus device, which can operate on the coils, whenever that device has to, whether it has to control the wall, actuator, or anything that just have a 2 states like on and off, 1 and 0, right? So that's why it's just a 1 bit. Now let's talk about the input. You can also call it as a discrete input, which is again just a 1 bit. So let's say if you have a device and your device is like a switch and you want to connect switch to your Modbus device and you switch on and off. So basically it's a 1 and 0. So if you want to take an input which is just a 1 and 0, the state either on or off, you can use a discrete inputs, right? So for coils is to turn on and off like walls or actuators or something, and discrete inputs will be used for a switches or something like that. Now the third one is an input register. So in the Modbus memory, you have input registers, and these input registers are, let's say, an analog input, which is a 16-bit, means 2 bytes. And this input registers will be used when you connect a sensor to your Modbus device and you want to store the data coming from the sensor. Now, sensor data could be much bigger sometimes, so that's why you have a 16-bit register, so to say. And then there is a holding register. So holding register is basically analog output, which is again a 16-bit. So if, let's say, in industry environment, you have devices like VFD or something, variable frequency drive, and you want to control by generating some value on it, then you can use this holding register. Now, the point here is these are the registers that will be found inside the Modbus memory of every Modbus device, and they have a dedicated address. Okay, they have a fixed address, by the way. So the coils will be found between the address 1 to 10,000. So when you look at any Modbus device, and if you look at the memory 1 to 10,000, then you will find the coils will be located. Then the discrete input will be found from 10,001 to 20,000. This is inside the memory region of the Modbus device. So in our case, if I write the firmware for this STM32 microcontroller, so it will be using the memory of the microcontroller, right? In the memory region. We'll get into that bit later. But just understand, like, these are the Modbus addresses that we are talking about. So if you want to read input registers, you basically read the address 30,001 to 40,000. If you want to read the holding registers, then you can read the address from 40,001 to 50,000. Okay, so these are like a Modbus address. And let me simplify these things. Let's say if you're working with any project and somebody give you some random device, okay, this is the Modbus device and you want to read the data from this device, then what you're going to do is you look into the data sheet of this device and you will look the addresses, the memory addresses, and then you write a C code and read that memory addresses in order to read the data from that Modbus device. That's how you write the firmware. I hope now you get the point why these addresses are very important, and these are the specific regions where you store a particular data, I mean the register values. So that's basically a Modbus memory areas, and you can also call Modbus registers. Now let's just talk about the Modbus RTU frame format, because in every protocol how you represent your data is very important, and when the data will be sent from master to slave or from slave to master, the data will be sent in the form of frame. That's why understanding frame format is very important. And the Modbus RTU frame starts with the slave address, which is 1 byte, and it ends up with the CRC, cyclic redundancy check. These are 2 bytes. And I mean, the start is a slave address of a slave Modbus device, and the end is a CRC. So CRC basically ensure the data integrity when you send the device from when you send the data from one device to other device. Because of the CRC value, you can ensure the data is transmitted properly and you have not lost the data in between. So first you send a slave address of 1 byte, then we send a function code of 1 byte, then we send the data. Data is from 0 to 252 bytes. We'll get into that bit later in detail. And then finally we send a CRC bytes. These are like a 2 bytes into the Modbus frame. Now let's take an example. Let's say I have a microcontroller like this one, and I want to write the C code in which I have to process the Modbus request. Okay, and this is, let's say, a frame that I want to send. Okay, or maybe I have a piece of software like a Modbus simulator, and I want to send the Modbus frame from my computer. So the first byte that I will send is a slave address. So let's say the device that I want to talk to have a slave address 0x11. Okay, so this is a slave address. Remember, the first byte is an address. Then we send a function code. Function code in this case is a 3. 0x03 is basically 3. Now, the function code in the Modbus tells the other device which receives what function we want to perform, right? So whenever the function code basically decides what the user wants to do, right? So let's say 0x03 is a function code to read the holding register. So that's why we use this function code. We'll get into that as we move on. And then we send the quantity of registers master is requesting. So how many bytes that the master wants to send to the slave, and then from what address, means the starting address from where we want to send the data. So let's say in this case, if we say we want to send 0, I mean, it's like a 4,000, I mean, 40,001. That's the starting address, if you remember. So for this is for the holding register. So the 4 will be 40,001 plus 4. So it will be a 40,005. Don't confuse when we will do these things with the live simulator. You will get the point. Now, let's just understand these things. We want to communicate to the slave device, which has an address 0x11. Then we want to read the holding register that stands for 0x03, which is a function code. Then we say that we want to read 4 registers, and this registers starts from 40,005 into the memory region, and then this will be a CRC high byte and this will be a CRC low byte, because there are 2 bytes in the end, and this complete frame represent the Modbus RTU frame. Okay, I will show you live. Don't bother about it. Looks a little bit complex in the beginning, but believe me, you will get it. So the last 2 bytes will be a CRC, and first byte will be a slave address or slave ID, whatever. And in between, you pass what you want to do. That's the function code. How much you want to read or write, means how many bytes you want to read, write, and what exact address you want to operate on. Okay, which address into the memory that you want to read and write, because that's where your variable will be stored, right? The value will be stored. Now, let's just talk about function code, because you don't know function code, and we talked about the frame where we used the function code already. So look at this, a list of function code. So 1, 5 means 0x01, 0x05. And there are a lot of different function codes. And this function code decide what you want to do with the Modbus device, like whether you want to read or you want to write, or you want to write the multiple data or read the single discrete input, or maybe the read multiple in the multiple parameters, whatever. So this function code represent the action, and then action on which place, I mean, whether it's the operation has to be done on the coils, or maybe the input registers, or the holding registers, or whatever, right? So let's just focus on one function code, because it's too complex if we take all the function code, and Modbus is very big protocol. We'll get into that bit later why I'm saying this. But let's just concentrate on the function code that we use in our example in the previous slide. That's a 0x03. And remember, I said when we use a function code 0x03, that means a function code 3, we basically interested in reading the data from the holding register, right? So we have an analog output value will be stored into the holding register, and we want to read the data from the holding register. So let's say if I write the firmware into this microcontroller, and for sure, because I am writing the firmware that understands the Modbus protocol, it will have the holding register. So using this function code 0x03, we will have the holding register. We will create an array as a holding register, and we will store some value. So when the master device sends a request to the slave device that it wants to read the data from the holding register, then this slave device will understand and accept the request coming from the master device. Okay, because we have implemented the frame which understand this function code 0x03. Let's go to previous slide. That's why you see the frame that we talked about uses the same function code, because I want to be very, very relevant when we do actual coding onto the device. So you get the point, like all these other function codes, this other numbers represent the other action, other operation, whether it's a read or write from the Modbus device, whether to read or write on the coils or a discrete input or input register, whatever. We are only concerned about the holding register, right? So we will be operating on the holding register inside the Modbus memory. Now, let's just talk about what project we want to do to demonstrate this Modbus capability. So you see in the picture here, I have this STM32 Nucleo board, and this STM32 Nucleo board has this STM32F303 microcontroller. And by writing the firmware, we will convert this microcontroller as an Modbus RTU slave device. And this microcontroller will use a UART communication, because remember, when we use a Modbus RTU protocol, we can use a serial communication, and UART is also serial communication protocol, right? Like UART, RS232, RS485. I just wanted to keep things simple. That's why I use a UART. So let's say if I have this microcontroller, this Nucleo board, and if I take the USB cable, I connect to my computer straight away, and now I'm ready to test the Modbus code, right? So that's why I prefer. So then this microcontroller over UART, I mean through the USB cable, will connect to computer, and on a computer I have this software installed called Simply Modbus Master. This Simply Modbus Master is a kind of Modbus master simulator. And from the master simulator, we will be sending a request through UART to this slave device. That's our microcontroller. And this microcontroller will send the response back to this Modbus master simulator, right? Simply Modbus application. So the Modbus master from the computer will send the Modbus request to the microcontroller, and the microcontroller will send back to the Modbus master simulator, Simply Modbus software, a piece of data that we request to this slave device, to this microcontroller. And remember what I said, we will create an array in which we will store the data from the holding register. So we will have a holding register, we will store some data, let's say 100 bytes, some dummy data we will store, some value in it. And through the Modbus master, we will request our microcontroller slave device to read the data. And the slave will respond back with the response, Modbus response. And then we will read the data onto the Modbus master simulator. That's a Simply Modbus. That's how the Modbus master can able to talk to Modbus slave in a request and response mechanism. That's what Modbus protocol is all about, right? How to do it, we'll get into that, don't worry. So if somebody wants to download this Modbus master simulator that I'm using, it's a Simply Modbus Master. You can download by going into the official website, and you will have a demo version. And in a demo version, if you do not have the license, then you can send 5 requests from the master. And then for the 6th request, you have to close the program and reopen again, and then use it again to send the next response code. So when you install, it looks something like this. So look at this application, how it looks. It looks a little bit old-fashioned, but it's very intuitive and very readable. I mean, there are a lot of different applications, but I prefer this one. So you can see the mode that we have to select in the application, Modbus Master application, as an RTU. Of course, if you use another Modbus standard like Modbus TCP or Modbus ASCII or something, then you select the mode as a ASCII or something else. Then because we have this a serial communication protocol we are using, so COM port and other settings like baud rate and data bit and the slave ID and the Modbus address and all other things that we can able to set into this Modbus master application. And then by simply clicking this or maybe pressing the send button, will send the Modbus request to the slave device. I will show you live, okay? So this is the program which I have written. It's called Modbus RTU Slave. Let's just go to the code and let's just do few things and see things in a live action. So I have this project here, and in the left pane you can see Modbus RTU Slave. And if I expand the source folder, then I have this main.c file. Okay, and in the main.c file, you can see I have this variable that says my slave ID. And you may remember that I said whenever, because this code will get uploaded onto this microcontroller, onto the STM32 nucleo board. And whatever it's written into the code, so let's say here in this line of code, it says like the slave ID is 17. That means this nucleo board, if this nucleo board is a Modbus slave device, then it's a slave ID is 17, right? I hope it makes sense, because that's what we wrote in the code. That's how we set the slave ID into the code, right? So first we set the slave ID, which is 17 in this case. Then you can see there is a while loop, and in the while loop we check some conditions here, right? So in the condition we check the position, data position, and the data position we check whether it's a 8 bits, because we assume that we would have an 8-bit to be received, because the size of the request, Modbus request, coming from the master. And then we check if the slave ID is valid. Okay, so if we get the slave ID, I mean from the master, when the request come, then it will be checked whether the slave ID is there. If the slave ID is there, then it goes inside the if statement. And in the if statement, you can see in the switch case, we are checking the content of this data array and the first element of the content that we test, and we check if it's a 0x03. Now you might wonder, okay, where is this data in variable, right? So there are a lot of variables been created here. So let me just take you to the header file first. And in this header file, you can see that we have created a maximum frame index variable, because you can maximum frame size will be 255. Then the holding register, like how much you can have, let's say 125 unsigned, and the holding offset is a 4001. Now this is where it's very tricky and very important for you to understand. If you remember the slide that I have showed, and then I talked about how this memory is very important, this addresses is very important, then look at this. We here, at least for now, we are interested in operating on holding register, because we want to read the data from the holding register, and this holding register is inside the microcontroller. Okay, and this holding register start with the address 40,001 to 50,000. Okay, that's why when you go inside the code, we have to define fc function code 3 holding register offset is a 40,001. Right, so we define in our code into the firmware of the Modbus device what is the address where your holding register will start. Okay, because you later then want to read the memory address to get the data. Now look at this, another array that's been created. It's called holding register. Remember I told you that we will write the microcontroller firmware, means inside this microcontroller we will have an array called holding register. Okay, and in the holding register, okay, this holding register, we have this many values. Okay, and now we are saying that when this holding register is inside the slave device, that means our microcontroller, the first element will be a 40,001. This will be a 40,002, 40,003, 40,004, and 40,005. Right? Let me just change this 40,005, 11420, and 40,005 and 40,004 and 5. Right? So it's 86, 82, 81. Okay, let me save this. So we have this holding register inside the microcontroller, and microcontroller is a slave device, and this is the data inside the holding register that the master wants to read, right? And this is the address that the master is interested to read. Okay, now there are a lot of different functions created. One thing, so this is just a header file where we have to just declare some variables and function, and this three defines are very important, and then this array is important because we are operating on holding register, and this 0x03 function code that we are using, that has to deal with the holding register inside the Modbus memory map. Okay, that's why we are just dealing with the holding register. And here is this a data in variable. So if I scroll up, you can see there is few more variable is initialized here. Like one is a response frame size, because sometimes it's very important when you send the response, then you have to know that what is the length of the data or the frame. And then this is where your data will be processed, like data in and maximum frame index +1, and then this is a data position based on how much bits you want to process. But the long story short, into the slave firmware, we have defined the slave ID, which is 17. Then we told in our slave firmware we are interested in holding register, that's a 0x03 function code, holding register. And we want to read the content of the holding register. And this is the holding register, right? And remember this two data that we modified. Okay. Now let me just, and there are few more things, but I think I'm already running out of time. The implementation of the CRC is in this crc.c file, and this is given by the Modbus specification itself in the documentation. So this code is not written by me. This is just a copy and paste from the official documentation. This modbus.c file here, I think this code is very important, but it's an implementation of how the data will be managed when the data will be received at, I mean, when the request will be received from the master, and all the processing is happening inside this modbus process register. I think there's no point to go in it, but just let me show you that when we upload this code, okay, I mean, let's say when I upload this firmware onto this microcontroller, this STM32 nuclear board will be an Modbus slave device. And let's talk to this slave device through our master simulator, right? So let me just click on this debug button on the top menu bar, and let's hope that the perspective will shift to the debug perspective. So let's click on switch. And now we are into the debug perspective. And you can see on the left pan into the live expression, I have this data in variable. Let me just expand it, and let me expand further. It may take few seconds because it reads from the memory of the microcontroller, right? And request and response takes a little bit of time. That's the reality of life. That's why the modern protocols, they don't use request response mechanism like in late 19th century, but they works in publish and subscribe model. But that's a whole different discussion. The request response, when we press the button here, it takes some time to get the response back from the device, right? So that's why you see some time it takes. Now let me expand, and you see the value of this data array is everything. Every element of this array is 0 because there is nothing. And this is basically a data variable inside the microcontroller. So because we have a lack of time, I would just click this resume button. So the code will start running inside the microcontroller. And then I'm going to open this Simply Modbus Master simulator. I basically use a proprietary tool from the vendor. Just for this demonstration for engineering hour, I'm using Simply Modbus, but it's still great software. So you can see the configuration. Let me just remove everything just for you. And now let me just now you see I put the number of register 4. Don't freak out, okay? Don't worry what is all the thing. Let me just talk about this first. So this Modbus application, Simply Modbus Simulator, is a master, and the slave is this microcontroller. I hope you can see on a camera, okay? And you can see it's in a debug mode. That's why this multicolor LED is blinking with multiple color, right? I hope the people who have used the nuclear board, they know that when it's in the debug mode, it's blinks the random color. So we first select the mode, and the mode is RTU. Then the COM port is 9 because my nuclear board is detected as COM9. Just go to device manager and confirm. Look at this, 9. That's why I set it 9. The baud rate 115200, data bits is 8. Pretty standard UART communication. Then we put the slave ID as a 17. This part of Modbus communication is very, very important. Okay, just concentrate for a few minutes. So slave ID is 17 because we want the Modbus master, this software, to talk to this slave device, nuclear board, and the slave ID of this nuclear board is a 17, right? and 17 decimal is 0x11. That's in a hexadecimal. So the moment I insert 17 slave ID, you see in the frame, this is the Modbus frame, and the first element slave ID is 0x11. So I hope you people are comfortable with working with the binaries in hexadecimal. So we set the slave ID 17, then we say, okay, we are interested in talking to the holding register. That's the function code 3. The moment we insert 3 here, it takes 0x03. Everything is hexadecimal here. And then we say we want to read how many bytes that we want to read. Let's say 8 or maybe 4. Let's say 4. So we are interested in reading 4 registers. And from for number of register 4 we are interested, and the offset is 40,001. Remember the table that I showed you in my presentation, the holding register is the 40,001, and the first will be counted 40,005 because we want to read 4 registers. So 40,001 plus 4 will be 40,005. That's why when we say we want to read 4 addresses from the memory, it's a 40,005, 40,006. So it starts with a 40,005. From 5, it will take 4. So 1, 2, 3, 4. Oh, I hope this is not too much. But let's go to debugger. There's no data yet. Let's take the master simulator. And because it's already running in the background, let me click the send button. The moment I click the send button, this request will be sent from the master to slave device. Okay, let me click on it. And the moment I click send button, you see in the debugger, we start getting some value. And the first value is the slave ID 17. You remember? Look at this, the slave ID 17. Then the second element is the function code 3. Then all this other garbage data. And you can't, I mean, I don't really have a time to go and convert into the hexadecimal to decimal everything, but let me just take you to this main.h header file. That is where we have defined this holding register. And look at this. This will be a first element, remember? 11420 that we modified. And this value matches to this, right? This one. The second will be 8281. So it's a 8281, 40,006 address. Similarly, you can read by yourself. We read 4 registers. I think 1, 2, 3, 4, right? And the last one will be 64892. And if you compare with this one, it matches, right? Now let me show you the magic. So let's just expand this. I hope you can see here. And you follow this, my mouse cursor. Look at this frame. This frame is a request that is sent by Simply Modbus Master Simulator. This 11030004, and this matches to the same frame that I wrote in my presentation, isn't it? Which I explained, right? So in a real time, we have sent this request from the Modbus master. That's a Simply Modbus application. And in a real time, we receive the response from our STM32 microcontroller right now. And this is the content of, I mean, this is the response that we received. And in the response, we receive all these values, right? Into this register, Modbus register address. And remember, just get this, what we received. The first one is a slave ID, then the function code, and this looks something different, 08. So what does this mean when we receive the response from the slave device, we also get the information how many bytes that we received. And if you count, let's say 1, 2, 3, 4, 5, so the last 2 is the CRC bytes. So this is the data that we have received. This black color in the background is same as this one, right? I hope you get the point. So this part is the Modbus request sent by a computer, my computer, to this nuclear board. And the second one, this is a response that is sent by this nuclear board to my computer onto this piece of software called a Simply Modbus. I hope this demonstrates the capability how you can use a Modbus Master to talk to Modbus Slave. In our case, our Modbus Slave device is our microcontroller. So we have implemented a Modbus protocol onto this microcontroller. That's why this microcontroller can able to respond to the Modbus protocol, right? Because this software is a Modbus client, right? Modbus application. Let's go to presentation. And this is where we left off. This was the code. Okay, and these are the few example I have taken as a devices which you often see in industry. So the first one is the energy meter from Schneider Electric, very popular. Pretty much any other smart energy meter these days, or maybe just an energy meter, if you buy, it comes with RS485 or Modbus communication. Then this is another product from the three-phase power measurement module from Wago. Then there's the sensor, which is also a Modbus. There are a large number of industrial sensors comes with the Modbus protocol. And then there's a flow meter from Rosemount. So these are just a few examples, but there are a lot of products out there. So that's it. I hope you have found this session educational and entertaining. And I'm looking forward to take a question if there is any around the Modbus and RS485 and all.
There are a couple of questions. I'll first start off by saying great job, Mesha. As always, really fortunate to have you as part of the community and presenting here on these types of topics. So a couple of questions from Salorm Lutsu. Are function codes specified in the standard, the Modbus standard, or are they device dependent?
See, this is very interesting question. So because I think you know that the Modbus is an open now. It's not proprietary anymore. So there are some function code which are fixed function code, which basically read, writes, like a basic thing. But you can customize function code by yourself. It's a complete open source, right? You can, if your product requires to implement a very specific function code to read some particular area to address, or maybe some variable to tune in, some really innovative concept, really some sensor which is out of the box from, let's say, Bosch sensor take, some time of flight sensor, whatever, crazy scientific stuff, then you can implement by yourself, right? The Modbus give you, because it's open, you can able to customize your own function code as well. So there are fixed function code, but you can customize your own function code as well, right? That's why, it's been so many years. I think before I born on a planet, this Modbus exists, and still to date now there are still people are making the sensors and industrial devices. So it gives you absolute freedom to the developer that you can customize anything and everything. And that leads to very important point. The simplicity of a Modbus is a blessing and the curse at the same time, because you implement the functionality, customized functionality to the level, to the degree where almost your product become a proprietary, unless you share somebody the addresses and the function code details, right? I hope this answers the question. Yeah.
That's great. Great
We can
advice there.
talk for whole day about it. It's a very big topic. Yeah.
Speaking of that, Rajasakar asked if there are any rule for 32 devices. I'm assuming he's meaning 32-bit devices. Yeah. Are there any specific rules?
I think the question is about what if one master can able to talk to a
Yeah, it's
32
actually
nodes.
now I'm looking back up further. It's like why up to 32 slave devices. So yes, it's any rule for the 32 nodes.
So I tell you to the person who asked this question, like I worked with so many protocols, and the way how many devices you can able to support, it depends on so many parameters, right? So in fact, I, I, I don't have the exact answer for it, but I did not even test it yet, the 32 maximum sleeves, right? But it's very hard to say, like, let's say let's take an example of another protocol. Let's take a Zigbee communication, right? The Zigbee never says when you build the Zigbee network from how one coordinator can talk to how many routers, right? So something like that. So I don't think, but in the Modbus RTU, there is a lot of mathematics out there, right, for calculating a lot many things. So maybe you can check in it. Yeah, I don't have the answer for that, but there's a lot of mathematics.
Here's a good question. Is the data, and this is back from Salorm, is the data size in the frame fixed for a device, or does the size change with each request?
Sorry, can you repeat the question? Like the data?
Sure. So is the data size fixed in the frame? So is it a fixed data size based on a device, or does the data size change for each request?
Oh yeah, I never work with such a situation, but I think as of now, I worked with the fixed data size when you send a request, when you read the addresses from the memory of the Modbus device. But I feel it's possible to operate on the data where the size of the data changes. It's possible. Let's say, let me give you one example. You have a device, let's say an energy meter, who, let's say, give you a data which might vary. I mean, the bytes may vary, the data size may vary, and the length will change, and it still operates on that, right? So sometimes you may not have some parameters out into the frame that you receive, but it's possible. Yeah.
Great. Last, just sort of high level question from Ajay Kumar. What are some key challenges you found designing at that application layer with Modbus for the first time? What are some key things to look out for when you're just getting started?
So when you're new and you are getting started, the maximum time you spend is to understand, this part, right? The addresses and the data. That's, I think, the last two question has to do with that only, right? Because these are the addresses. On this addresses, what is the size of the data is sitting there? And the last question was like, what if the data size changes, right? Because then your frame size changes, right? So when you're new, it's really confusing, like which area, the coils and discrete inputs and input registers where it belongs to. And then one of the interesting thing I can share with you, and somebody on LinkedIn also posted this question, like, in the world of Modbus, because its simplicity and the freedom that it provides, people give any address to any parameter. So let's say in the coils, let's just take an example of holding register, because we worked with holding register right now. So just stay with it. So the address starts from 40,001 to 50,000. So let's say if somebody, some decent person, when start writing an application, he will first variable value, he would probably try to stick with the first address into the memory, probably, let's say, for example, 40,001. that temperature sensor data will be on, let's say, maybe the frequency parameter will be on the 40,001, the next frequency parameter will be a 40,002, and next frequency parameter will be a 40,003. This is like a common sense in the sequence. Now, because the Modbus give you freedom that you can choose any memory region for storing your value, whatever you choose between 40,001 to 50,000. So some idiot would gonna go and get it, like they will start with from 40,000, let's say 10 to next 20 parameters. Now, the problem with such a addressing, some people does this kind of products knowingly, because it makes it difficult for somebody who try to read the data from your device without having the official documentation. Now, what happens is with this kind of things, you have to, when you work with any Modbus product, in the early days, you have to do a lot of trial and error, right? Reading the Modbus addresses and then try to guess and gauge what data is coming, especially the product, the devices, sensors where you lack the documentation, right? So let's say you buy some random Chinese sensor and the documentation is in Chinese, or maybe doesn't exist, or maybe I mean, it depends, like not just pointing to Chinese, but any even Indian, or maybe it's a company, let's say somebody from somewhere from Europe and doesn't have the documentation, or maybe it's a legacy system, there is nothing. So that's the pain that to work with the Modbus addresses. And then coming back to other point was the size of the data is also matters. Like somebody asked this question, what if the size of the data varies in the real time? And this happens a lot, because when you read the data from the Modbus device and you don't know what is the size of the data that you, I mean, because you just do guess and work. So you sometimes create, let's say, an array on which you want to store the sensor value, and that value is not, that array is not good enough, right? Or that variable size is not good enough to handle that much data, right? So this happens. So this is a little bit tricky in the early days. Yeah.
Very good. Well, that brings us to the end of the time we have for today. Obviously, also always great to hear from Ramesh, and luckily for all of us, there's a part 2 that's coming up on Friday, April 11th. Same start time, 1500 UTC. So do the math. You can figure out what that means for you. And Amesh, during that set presentation, is going to be going over one master, multiple slaves, master slave firmware, events and polling rates, and then he'll also have a live demo as well. So make sure you sign up for that. I dropped links in your respective platforms. So we'll look forward to seeing you then, and have a great weekend. Oh, one last note. Thanks again to Embedded World for giving us an opportunity to exhibit there. It was a lot of fun, great success, and we're looking forward to being at many Embedded Worlds in the future. If you do not know, Embedded World is sort of a global event series now. You can check it out in Shanghai, in Anaheim coming up in the fall, and then of course in Nuremberg. So if you go to embedded-world.de, you can find out more information. So thanks a lot to them. Thanks a lot to you, Mesh, and thanks for everybody showing up. And we'll see you next week.
Thank you. Bye-bye.
Bye.